now we move on to L10, and we're going to do the moment of inertia of a rectangle. The door, about this axis, like if you're opening the door there, what's going to happen there. So let's do here the door, and if we have a z-axis like this, and we have the door here, and your hinges, along here. Let's give this distance A, and we'll give this distance B, A by B, and here we'll have a nice little strip, and for that strip, this strip will be, let's go ahead and put in an x-axis here. I'm gonna call this x. Now, if the y-axis in this case would have to go into the page if you want a right-handed system, we're not gonna need that y-axis. But if you have the I, which is the x, and then you have the k for the z, you're going to need j for y going into there, so you take I cross j, you turn I into j, you're going to advance up. That's a right-handed coordinate system. I always like to have one of those. So this here is x to get you out to here, and this little thickness here is dx, and then this is a little dm. And since we can think of this as like a surface, a flat surface, we'll use the area density, sigma, as the total mass divided by the area, A times B. So the little moment of inertia differential is going to be x squared times dm. But dm is going to be the density times the area of the strip. The area of the strip is going to be A times dx. So A times dx. So you can write that down as dA is little a times dx, and that dm is sigma times the differential area, and the differential area is A times dx. And that is what's going up in here. That's what's going up in here. This is your dm. Your dm. So that means that we're going to do an integral here. And let's go ahead and write the di one more time. And let's go ahead and collect the constants, put them out front, and then we have x squared dx. And now we can put in what this is. A is going to cancel, and you're essentially going to get here m, big M, over b. So the integral that we're doing, and we're integrating here from x is going to go from 0 out to b. We have big M over b times x squared dx. So we have everything here. And this integral is very easy to do. The m over b can be pulled out, it's constant. And you go from 0 to b, x squared dx. This is going to be x cubed over 3 from 0 to b. So this is going to be m over b, and this is going to be b cubed over 3. This is going to be 1/3 mb squared. Now, you might recognize that. Let's go ahead and put that down over here, 1/3 mb squared. Because when we did the pencil, when we did the pencil or the rod about the end, we got 1/3 ml squared for the moment of inertia. But see, this can be thought of as lots of pencils, lots of rods. And each rod would have, here, if you summed up the I's for all those rods, you would have the sum. They all would have 1/3. They would have a little bit of mass, mi, and then they would have the same distance, which is in this case b squared. But see, then 1/3 is constant, b is constant, all the rods are the same length. So this is just saying sum up the masses, which would be capital M, which is what we got here. So really, we didn't really have to do this. We could have just noticed that and then written down the answer. But it was good practice. Next, we do the hope chest. And the hope chest has the same formula because you're basically opening the lid about that long axis or an axis. Really doesn't matter which axis you use, you just switch A and B. So we basically have that formula already. The hope chest is the same formula. Just remember that this B is the measure that's away from that axis. So there's the B. And this other one we called A. Well, we can do a revolving door. Now, in the case of a revolving door, I'm going to make an idealization. Say we have like a flat rectangle and we want to spin it about the center. All right. So if we do that, we have our rectangle like this, and we want it to go about the center. Now, actually, that's going to be about the center of mass. That axis goes to the center of mass. So here you have A. Here you have B over 2 and B over 2. So we have the same width. And we use the parallel axis theorem, which says that I is equal to I of the center of mass plus the mass times how far you're away from the center of mass, that axis. So here, D is B over 2. That's how far we're going to be away when we're doing, and this is the edge. So this is the edge one. This is the one we already found here. So the moment of inertia about the edge is the moment of inertia about the center of mass plus the md squared. But I want to find the center of mass one, so I'm kind of like going backwards in a sense here. So I have 1/3 mb squared is I center of mass plus m d squared is going to be b squared over 4. We're squaring the d, get b squared over 4. So the center of mass result is 1/3 minus 1/4 mb squared. And we've seen this before. This is 4/12 minus 3/12, which is 1/12. And we get 1/12 mb squared. And you probably recognize that is the rod through the center. In other words, if you had a rod like this through the center, and that was the mass of the rod, we would have this formula. So just like the other analysis we did, we could think of this as lots of rods where each of them has a portion of that mass. And since they all have the same B and you all have the same 1/12, if you add them all up, you'll just get the total mass in there in the formula. Okay, here's a good one for rotating the rectangle, a table that rotates. So here, in other words, we're going to go put the center right there through the center of mass and rotate it that way. So this way we're going to orient it a different way. So the rotating table, we're going to look at something like this now, where we're going through the center of mass, literally it's itself right there, like the point. So this is the z-axis, this is the y, and this is the x. It's a right-handed coordinate system. And this distance here we'll call B, and this distance here we'll call A. Okay, it's a little thickness there like that, like if you want to sketch that in. Now, the moment of inertia about Z is going to be the moment of inertia about X plus the moment of inertia about Y, which is the perpendicular axis theorem. Now, what is the moment of inertia Ix? Well, Ix, that's going around this way, around the x-axis. So that's b over 2 out to the side. That's the one that we did here, b over 2 out to the side, and we have that answer here. So this is going to be 1/12 mb squared. Now, what about going around the y-axis? Well, if you go around the y-axis, then you have a over 2 and a over 2 on either side. So you have a instead of b. So this one is going to be 1/12 ma squared. So about the z-axis through that center, we have, look at this nice formula, 1/12 ma squared plus 1/12 mb squared. Very, very nice. And we can factor out the common terms and have 1/12 m a squared plus b squared. And that's the rotating table case. And if you want, you could then kick it over to here to have it go about that midpoint, or you can kick it over to the corner and have it go around the corner. So if you wanted to have it around, say, the corner like this, then we use the parallel axis theorem and kick it d away. So if we're going to go for that corner, we would have I center of mass plus m d squared. Now the d squared here would be, you're looking at going b over 2 and a over 2 and b over 2, to get over there. So that would be here a squared over 4 plus b squared over 4. So you would simply take this thing and add the 1/4, but we know that when we add 1/4 to 1/12, we've done this before, we have 1/12 plus 3/12, which is 4/12, which is 1/3. So we're going to have here about the corner to be 1/3 m a squared plus b squared. See how easy it is to do all these complicated cases? You simply take the center of mass, result one here, and kick it d, and that d has the a over 2 this way and the b over 2 that way. It's a right angle. So you're looking at the Pythagorean theorem. You're essentially adding here the 1/4 to the 1/12 to get the 1/3.